formal definition of independence, what does it mean? Well, we've already hit on the idea of independent events several times this unit. We talked about the fact that independent events are events in which one does not affect the other, like rolling a coin or flipping a die. They don't care what happened on the other thing. But I also mentioned independent events when we were talking about dependent events. And not only dependent events, but also conditional probability, because conditional probabilities imply a dependent situation. So the formal definition of independence, it says if A and B are independent events, oh no, excuse me, not if. A and B are independent events if the occurrence of one does not affect the occurrence of the other. Well, we got that. We know that. Here's what this means, and this is a really important fact, and for some reason, it just kind of escapes students. Wow, okay, that was a star, but my board. Let's try that again. There we go. This means that the probability of A given B, or A given not B, is legitimately just A, because A doesn't give a flip what happened with B. They're independent. And that's what I tried to show you the other day when I was like, well, let's talk about it, when I was showing you the formula. When I was showing you the formula for dependent events, no, not dependent, conditional probability. Remember, because the probability of A given B is equal to the probability of A intersect B divided by the probability of B. But if A and B are independent events, then the probability of A intersect B is legitimately just the probability of A times the probability of B. So when you divide by the probability of B, they cancel out, and you're left with just the probability of A. So that's a pretty powerful statement that students often overlook. Now, talking about conditional probability, since the probability of A intersect B can be written as the probability of A given B times the probability of B, and remember that came from the formula for conditional probability system, is like probability of A given B is equal to the probability of A intersect B over the probability of B. If you just multiply both sides by the probability of B, that's where this statement comes from. That was one of the things that was written in the rectangles from conditional probabilities. Okay, well this tells us A and B are independent events if and only if, and this means it's true backwards or forwards, the probability of A intersect B equals the probability of A times the probability of B. And we already knew that. That's an earlier lesson. So today we're going to be tying those thoughts together, and we're going to be proving whether or not events are independent using these knowledges. Knowledges? Is that a word? I'm not really sure, but it felt right. It felt good as I was thinking it. Using this knowledge, feels like these several points of knowledge. Okay. When two coins are tossed, event A is you getting two heads. When a die is rolled, event B is you getting a 5 or a 6. So let's first, before I do anything, the probability of A happening. Well, that's two coins, and I'm trying to get heads and heads. The two coins are independent of one another, correct? So the probability of getting two heads is 1/2 times 1/2, which is 1/4. So the probability of event A occurring is 1/4. Now, event B, probability of event B, is you rolling a die and getting a 5 or a 6. Since it's impossible to roll a 5 and a 6 in a single roll, there is no overlap. So the probability of this or statement is legitimately just the probability of a 5 plus the probability of a 6, which is 1 out of 6 plus 1 out of 6. 2/6, or what does that reduce to? 1/3. We were told to show that A and B are independent events. Fine. The probability of A times the probability of B is 1/4 times 1/3, which is 1/12. Now, these are only independent events if the probability of A intersect B also equals 1/12. So we're going to solve this one actually a very rudimentary way. We're going to use the dot plot. I'm going to list out the sample space. All 24, all 24 possibilities using a dot plot. So here is heads, heads. Here's heads, tails. There's tails, heads, and tails, tails. And on the left axis is going to be 1 through 6. 1, 2, 3, 4, 5, 6.
So why did you multiply the getting two heads and not add them?
Because it's an and statement. Heads and heads. Anytime it's an and statement, you have to multiply. Now I have to make my 24 dots. The most time-consuming part of this question is creating this diagram. And I don't know about you guys, but it looks like absolute trash on my paper. Is it almost over yet? Oh my gosh. 24 dots later. I think in the future I should just put this diagram on the notes for you guys. Okay, here we go. I know I'm supposed to put the vertical and horizontal lines through them, I just don't feel like it, all right? Each blue dot represents one outcome. There are 24 different outcomes. We are trying to figure out what the probability of A and B happening is. So let's figure out how many times we have two heads and the number 5 or 6. Well, here's two heads and the number 5 or 6, and well, here's two heads and the number 5 or 6. And that's it. So 2 out of the 24, come on, active panel. Any day now. Come on now. Thank you. 2 out of 24 reduces to 1/12. Hey, look. The probability of A and B happening was the same as the probability of A times the probability of B. Since they are the same, these are independent events. Because two events are only independent if the AND statement has the same probability as the multiplication. I mean, that one's common sense, but what we just did proves it. Understanding what we're doing? We are trying to show that when you multiply the probabilities, you get the probability of the AND statement occurring. If they are not equal, then they are not independent. Comfortable with that idea? These two were equal, so they are independent. Can I move to harder questions where they say extra stuff? Everybody's ready to at least understand the concept? Great. All right. That's the only time I'm going to use a dot plot. The rest of the time we use set theory. Suppose the probability of event A is 1/2 and the probability of event B is 1/3. Oh, also, the probability of A or B is P. Oh, find P if. So this is two different questions that are not related at all. You do part A, you reset your brain, then you do part B. I wonder why he was making such a big deal about that. Okay, so suppose this information is true. Find the probability of the union if A and B are mutually exclusive. What does that mean? What does mutually exclusive mean again? They don't overlap. For some reason, ExamView is trying to open on my computer. I think the calibration's off on my active panel. That means they don't overlap. Well, since they don't overlap, the probability of A union B, I'm going to write the addition law of probability. It was supposed to be the probability of A plus the probability of B minus the probability of the overlap, but mutually exclusive implies that this equals 0. So the probability of the union is legitimately just 1/2 plus 1/3. Common denominator 6. So the probability of the union is 5/6. That one's pretty easy, right? We like mutually exclusive. Makes life easy. Part B says A and B are independent events. Remember, mutually exclusive and independent are two completely different ideas. Yes, Anastasia? That's the common denominator. 1/3 is 2/6. I was just common denominator. So mutually exclusive and independent mean two completely different things. Mutually exclusive means cannot overlap. Independent means don't affect one another. But that doesn't mean they don't overlap. It just means they don't affect one another. Two completely different ideas. So part B, you can no longer cross out the probability of the overlap. Well, we're still trying to find the probability of the union. So here's the addition law of probability. But you were just told these things are independent events. What does that imply? Independent events. The probability of A intersect B is found through multiplication. That's what it means to be independent. That's what it says right here. If they are independent, the intersection is found by multiplying. Okay. So now we just plug in the things we know. 1/2 plus 1/3 minus 1/2 times 1/3. Well, we already know that 1/2 plus 1/3 is 5/6. So this says 5/6 minus 1/6, or 4/6. You can reduce it to 2/3 if you want to, but you don't have to. I'm going to go ahead and tell you, recently finished your test, and there is a question on there that made me scratch my head for a little bit. But I'm dropping you a hint right now. And it's important that you understand that if you are told two events are independent, that tells you that in this addition law of probability, there's a multiplication at the end. Once I realized that, I was like, oh, okay, gotcha. But it took me a minute to think about it. And we all know that when we're stressed for time, brains don't work properly all the time. So I'm warning you now.
Are we gonna have these on the test, like the probability of A plus probability of B minus probability of...
You mean the reference sheet?
Yeah.
Sure.
Is that gonna be on? Is that on there?
Yeah.
Oh, okay.
Yeah.
Wait, so all these formulas
Okay,
are
because I'm
all
not gonna remember it.
Yes.
Oh.
Yeah, they're all on there. And yet, I am confident that I will not be eating a pin. How about that?
How about let's make
If we get an A average.
No average is not acceptable. It's not an A average is not acceptable.
Bree just said she wants to see
That's
you
a separate
die.
thing.
What's that?
It's a separate thing to replace settlers of Catan if we get an A average.
How are we going to play Settlers of Catan? We have to practice for an IB exam. I tell you what, if everybody in the room right now, as soon as I say it, doesn't even have to think about it, can tell me what sine of pi over 2 is, we'll play Catan. 1, 2, 3, go.
0.
Wow, whole bunch of wrong answers. It's 1. So many people said 0. Like,
She goes,
7, a number that sign cannot equal.
Like, I know, but like, even if you were doing it that way, that doesn't.
So many people said 0. That was wild. I really wasn't expecting that many wrong answers, but
I didn't know, so I just heard
That
it.
was
I
so
thought the first
unfair.
time
That's just so quickly.
I wish we had like mind communication, so we could just.
How about cosine pi over 2?
hive mind. Okay. Whew, here we go, guys.
He said telepathy.
Okay. All right. Now, there it is. Now, I write kind of big, but there it is. All right. Yes. I mean, no. Thank you. Thank you for making me laugh today, Bria. It was a hard morning.
It was a hard one. Did you fall down the stairs?
It was a hard night.
Oh.
It's personal. Okay, so
He's not friends with us. You can't tell us.
the probability of A. Now, okay, now here we go, guys. You're gonna have to go with me on this one. Oh, and by the way, there is a part C that I need to add that for some reason I didn't type. But part C says, are they independent? So I just wrote that on my paper. Independent? Question mark. That's part C. Okay. Goose fraba. Here we go. Suppose the probability of A is 2/5. The probability of B given A is 1/3. And the probability of B given A naught is 1/4. Find some stuff. Whoa. No, you cannot tell that. Because you have to prove it using math. Ah, so what she's noticed is that the probability of B given A does not equal the probability of B given A naught. Automatically you know that they are not independent. But you have to say that. So you have to say because probability of B given A does not equal probability of B given A naught. If they were the same, then yeah, that would be independent. Because what that tells you is that it didn't matter that A happened or not.
Wait, if they're the same.
If this number had equaled this number, then what that means is B didn't care if A happened or not. That's what that means. Then they would have been independent. But since those are not independent, you can answer C right off the bat and go, oh, no, they're not independent. However, I'm going to show you how to do it another way. I wonder why. I mean, I don't know why I would want to do that, but I'm definitely going to want to show you another way. I mean, I don't know if my people at home can see this, but I'm going to show you another way. Okay, so. Do you know what would make this question a lot easier? At least it did for me. A picture, a Venn diagram, yeah. So I drew a Venn diagram. I think that some people in this classroom partake in too many trees.
Bruh.
Maria.
Oh.
All right.
You got collapsed into the tree right there. The branch that fell on your head.
So, can we right off the bat fill anything in? No. Shucks. How about that? I was hoping it would help. So I tell you what we're going to do. Let's do some math, and then we'll maybe fill in some Venn diagram later. It wasn't necessary, but for some reason, well, I know why, set theory is difficult for me. The picture makes it easier just because it reminds me what places I'm looking at. That's what it does for me. So this picture, I go, oh, that's right. This place represents A intersect B. This place represents A intersect B naught. This place represents B intersect A naught. See, just saying those terms is hard for me. seeing those terms, I go, oh, that's right. Yeah, I know what that means. I don't know why. That's just a me thing. I mean, I need it. I need it. Part A. Let's find the probability of B. Okay. I see that I have given information. When I say given information, I'm sorry. Given A, meaning conditional probabilities. I see I have conditional probabilities. I was given A, I was given A naught. So I started mine when I did this with this. The probability, this is for part A. The probability of B given A. I'm gonna write the formula for this. That is the probability of B intersect A divided by the probability of A. Oh, A naught, sorry. Boop.
What is different changes in the formula?
Hold on. No, the formula, all the A's just become A naughts. I'm sorry, I'm just looking at my paper because when I did this, I accidentally did part B first. So then I put numbers on it telling me what order to do them in for you. And I numbered my own crap wrong. Or did I not?
I think
Oh, shh,
goes on it.
shh, shh. Just trying to make sure that I have the right order here before I go any further. I did that for a reason. I see that reason. Did I use that knowledge somewhere else? I did. Okay, I'm all right. I thought I numbered it wrong, and I didn't. I'm not going to lie. They shouldn't have primes. I'm not going to lie. I never teach this lesson without doing all the questions the day before, because this is hard for me. I had these notes completed already, but I printed them out and made sure I could still solve the questions. This last one is hard for me. Like I said, I ended up doing part B first. It was just easier for me to find B first. But you didn't have to, and I want to do it in the order that the book said to do it. Why, Mr. M? Because, to be honest with you, this example was in the old textbook, and it had parts A and B. In your textbook, it only has 2 parts, but they got rid of this part. But I think it was good knowledge, so I left it. They replaced it with are they independent? I wanted all 3. Okay, there. Explanations are done. Okay, so this is a true statement. What that means is I could find a piece of my Venn diagram right now. And that is because I know the probability A as a number, and I know the probability of B given A as a number. I can find the probability of the intersection right now. If you multiply both sides by the probability of A, you get that the probability of B intersect A, which is the same thing as saying A intersect B, is the probability of A times the probability of B given A. And this is the center. This is the overlapping part.
Wait,
What?
I'm sorry. I just
Here, I did this. I just multiplied that to both sides. It's yeah. I put the thing I was solving for. I put on the left so I could try to be out of the way. It's not wrong to write it the other way. I just was trying to get out of the way because I'm in Katie's way a lot. Yes.
So is it A now or is it A?
No. It was supposed to be A. I did it right the first time. Yes.
I think I'm gonna lost my phone.
It's in the pouch. My charging station.
Okay.
You left it on the table. That's where I put it.
Thank you.
You're very welcome. Okay, we know the probability of A. The probability of A was given to us. It's 2/5. And we know the probability of B given A. It was given to us. It's 1/3. That means the probability of the intersection is 2 out of 15. And because I don't do very well with set theory, I put that information in my Venn diagram because it helps me keep that organized. This is why I could not be an actuary. I require the images. Okay. We still haven't done part A, by the way. We're not done yet. All we did was find the probability of the intersection. Cool? Cool. Next step. Let's use the other information that we were given. Let me scroll down so I have space. We were also told about the probability of
So you need that information to find the probability.
yes. We were also told about the probability of B given A prime, correct? Okay, I'm going to use the formula for that. That is the probability of B intersect A prime over the probability of A prime. Why would I do this? Here's why. You can't be just floundering. You have to understand why I took this step before I move on. We're trying to find the probability of B, right? That means I'm trying to find the probability of this circle. I already know a piece of it. If only I knew the other piece, all I'd have to do is add those two probabilities together. And this piece over here is where B intersects with everything that is not A. So that is why I'm trying to hunt that down. And then I noticed, oh, I was given some knowledge about B and A prime. See? And that's why I went immediately to this formula right here. Because I can isolate the probability of B given A prime by multiplying, like I did on the top, multiplying both sides by the probability of A prime. Again, I'm switching it around because I like the thing I'm solving for to be on the left. So if I, because, no, it's fine. Because B intersect A prime is this area of the circle. That's where B has in common with things that are not in A, right? If I knew this green B intersect not A, then I could add that to the 2/15 and I would know the answer for the probability of B. And once I wrote that, I said, oh, well look, there is information that was given to me that deals with specifically B and A prime. So then I wrote the conditional probability formula for that and realized that I could isolate the green thing I was looking for simply by multiplying both sides by the probability of A prime. So here's the probability of the green thing I was looking for is found by multiplying both sides by the probability of A prime. The second one, probability of B given A naught, that was handed to us in the directions. That's 1/4, right? Let's see who's thinking today. What's the probability of A naught? 3/5 it is. How'd you know that? Because A is 2/5. Not A must be 3/5. Yeah. So the probability of this intersection is 3/20. This intersection is 3/20. So to find the probability of B, you add those two fractions. Two 2/15 plus 3/20. Common denominator is 60. So multiply by the 4 on top and bottom again. 8/60 and times plus 9/60. Probability of B is 17/60. Woo! What's that? We finished part A, like a boss. Oh, look, we did part B at the same time. How about that?
No way.
Yeah, part B was the green probability, 3/20.
Should we show that separately on the?
No, you don't have to.
Oh, the 8 years.
Oh, I'm sorry. Man, crud, I gotta do more work. Oh, yeah, see, stupid set theory. This is A intersect B naught. I'll be all right.
But at least we know what B naught is.
What's that?
We know what B naught is, or you have probability of B. Right?
Yeah, did I do it that way? How did I do it? I did A,
It's gotta be A.
yeah,
plus-
yeah, that's exactly how I did it.
We just have to subtract.
You subtract it, yeah. Because what we know is that, where is it? 2/5. Probability of A is 2/5, right?
Yeah, so
And we know the probability of B.
it's 40, or. Is 2/5 including 2/6?
The 2/5 is including the 2/15. So what you're doing is, I think you were doing it the hard way. Harrison, what you were saying would absolutely work, but you're working way too hard using B naught, okay? You're not wrong, but it's way too hard. But Alberto, I think he's got the easy way. Alberto just said, does the 2/15 count as part as A? I said, absolutely. So since the 2/15 is part of A, and you know that A is 2/5, you just do 2/5 minus the part that was already given to you.
Oh.
Isn't that what you were getting at? Yeah. So it's 2/5 minus 2/15. So the probability of where A intersects with B naught is going to be, well, we know what A is.
Yeah.
And we were already told that the intersection area, or we found that the intersection area has a value of 2/15. So you just subtract. And that's how you figure out what's left in the crescent, which is 6/15 minus 2/15 or 4/15. Set theory, yuck. It's hard. Yes.
I like when we did other things, I like did that myself before we found
Part B.
the answer to A, so yeah.
Yeah, I did the same thing. When I did it, and I was like, oh, true, and I started working, and I was like, oh, whoops, I found the answer to part B first. But then I was like, all right. And here's the thing, though, but finding that didn't help you get to the other answer at all. So that's why I went ahead and did it in the order they asked me to do it, because I realized, even though that was much easier, I realized it didn't help me at all. So, yeah.
I'm just trying to like figure out how to write this in like little terms.
Yeah, little terms, gotcha.
Yeah. So basically, you have like probability of A minus the probability of is it called A intersect B when they're just like
A intersect B naught. Oh, A intersect B, yeah.
thing in the middle.
Yeah, here's what we did. We did this. So you're trying to write a rule, I guess. The probability of A intersect B naught is the probability of A minus the probability of A intersect B. I think that's what you were trying to do. That's what we just did. We just said, okay, this is the crescent part of A is all of A minus the intersection. That's what that says.
So the crescent part, so it's like everything that's
Yeah.
looks like that.
That's why I keep calling it a crescent.
Yeah, I know.
I don't know what else to call it.
I like it. Just call it the crescent because I don't understand the other part.
Yeah, we're done. It's 4/15. Yeah, but she was trying to write a rule. She was trying to understand a rule, and I was like, yeah, this is also, and you can do the same thing for B. The probability of B is the probability of B intersect A naught minus the probability of the intersection. Or, no, I said it backwards. Strike that, reverse it. Probability of B intersect A naught equals the probability of B minus the intersection. Yeah, here's this. This is the crescent part of circle A. If you want to know the crescent part of circle A, you take the entire circle and then you just subtract the eye shape, the cat eye in the middle.
Right.
And that, so she was just writing a rule.
Subtract A intersect. Okay.
Don't worry about it. You don't have to have that memorized. You don't. This is just what she was trying to do.
No, but I need to understand this.
Okay. Set theory's hard. I mean, you see the way I struggle with it. No joke. I redo these notes every single year because for some reason, set theory just doesn't stick. It's hard. It is hard. I redo them every year. So I've done this question like 5 times, and I still have to look at my notes when I'm doing it. Like, it's a hard question. And the last one is, are they independent? Now, we saw through the bull crap. Well, she saw through the bull crap at the very, very beginning and found out that they were, in fact, oh, hold on. I'm tied up. They were, in fact, not independent because of given information, but I'm going to go ahead and do it a different way. I'm going to do it a different way. He said with his eyebrows way up high. Okay. Here's what we know. The probability of B, we found the probability of B to be 17 over 60. Correct? Weren't we given the probability, didn't they tell us the probability of B given A? Right. This was given to us. It was 1/3. Here's what this tells you. A happening clearly affected the probability of B happening. Because if they were independent, these would have been equal. So you just say, since the probability of B does not equal the probability of B given A, dependent. And this is a very important concept, realizing that the given statement does or does not affect the result. And I did it another way as well. This is what the book did. I did it another way. I used the definition of independence. I used the definition of independence. The probability of A times the probability of B is, okay, well, we know the probability of A, it's 2/5. We found the probability of B, it's, where are you, 17 over 60. That's a big number on the bottom. That is 30. Oh, you know what I did? I reduced it. That's why. What's that? Nah, just leave it right there. Thanks, Junior. Appreciate you. The probability of A, there it is. Yeah, the probability of A was 2/5, right? Okay. This gives me 34 over 300, but you know what? I don't want to have to do that. I could just reduce right here. I can call this a 1 if I call this a 30. There. That gives me 17 over 150. Cool beans with that? We good with that? And we found this. The probability of the center. The probability of A intersect to B was 2/15. Since those are not equal, not independent. That's using the definition of independence. Come on, active panel, please keep up with me. Oh my God. Oh, look, we're crashing active Messiah. Fantastic. What in the world is going on? Do you see this? Jesus. Here we go. So since probability of A intersect B does not equal the probability of A times the probability of B, dependent. So we saw how to prove them dependent or independent more than one way. We actually saw 3 ways, thanks to Kennedy. There was a 3rd way that I didn't even catch. But yeah, they gave it to us right there at the beginning because the probability of B given A was not the same as the probability of B given not A. And they have to be in order for them to be independent. So yeah.
And they also have to be equal to the probability of A.
No, they have to be equal to the probability of B.
It says on the front.
No, that's because that one's A given B, A given B not.
And then when it's reversed,
Mm-hmm.
the other one.
Yeah, and if you reverse it, you reverse it.